This is section 5.9, hyperbolic functions. A hyperbolic function is a certain class of exponential functions. This idea of a hyperbolic function arose when you compare the area of a semicircular region, which goes to the trig functions, with the area of a region under a hyperbola, which leads us to the hyperbolic functions. So, because it's related to a hyperbola, hence the name hyperbolic functions. The integral for the semicircular region involves an inverse trigonometric function, arcsine of x. The integral for the hyperbolic region involves an inverse hyperbolic function, inverse hyperbolic sine of x, which is written as sine followed by an h to make that hyperbolic sine inverse of x. And notice the similarity in the two integrals on that slide. The integral from -1 to 1 of the first one gives you something that involves arcsine, and the second one gives you something with 1 plus x squared under the radical that involves hyperbolic sine, the inverse of it. So let's first of all talk about, before we get that far, just what are the hyperbolic functions. Well, as I said earlier, they are a special class of exponential functions. Hyperbolic sine of x is defined as e to the x, hence the exponential part of this, minus e to the opposite of x over 2. Hyperbolic cosine of x, we'll remind you of that one. It's e to the x plus e to the opposite of x over 2. And those are the two main definitions that you're going to need to know going forward. The rest of them are defined in terms of other hyperbolic functions. For example, hyperbolic tangent of x is hyperbolic sine of x divided by hyperbolic cosine of x. By the way, you can't really see as well as I would hope, so just so that you know, when you write hyperbolic sine, that's the name of the function, and it's followed by an argument, x, so that instead of sine of x, it's hyperbolic sine of x. S-I-N-H is hyperbolic sine. So the parentheses are understood, generally speaking. Anyway, hyperbolic cosecant of x is 1 over hyperbolic sine of x. And we don't want that to be 0. And if you look at the definition, e to the x minus e to the negative x is 0 when e to the x and e to the negative x are the same number. And that happens when x is 0. E to the 0 is 1 minus e to the opposite of 0, which is e to the 0, is also 1. 1 minus 1 is 0. So we don't want to let x be 0 here. Now, if you're thinking about hyperbolic secant of x and think the same thing is going to be true, it's actually not, because the only way hyperbolic cosine of x could be 0 is if e to the x and e to the negative x were both 0, which is impossible. So there's no such restriction made on hyperbolic secant of x. X can be any real number. And then hyperbolic cotangent of x is 1 over the hyperbolic tangent of x. And we don't want that to be 0. The only way that could be 0 would be if hyperbolic sine of x is 0, which we've already discussed. That happens when x is 0, so we cannot let x be 0. Otherwise, we'll be dividing by 0. Now, if you look in the next page, there are the graphs of those 6 functions, their domains and their ranges. So take a good look at those, and the accompanying dotted line graphs are interesting because you can see how like hyperbolic sine of x falls between those two functions, f of x equals e to the x over 2, and g of x equals the opposite of e to the, I think that's negative x over 2. It's so small I can barely read it. But at any rate, kind of gives you an idea of how those come to be and what the graphs look like. It's just kind of interesting. So just take a look at those. So as I said, yeah, it was e to the negative x on the next page. If you added those two functions, you'll get the hyperbolic sine of x, which means that the result is between those two. Likewise, the graph of hyperbolic cosine of x can be obtained by adding the corresponding y-coordinates of the exponential functions f and g, the same two. Well, I'm sorry, h doesn't have the negative in front of it because it's plus for hyperbolic cosine, right? And so if you add the ordinates of those two functions for any x, you'll get the resulting hyperbolic cosine of x graph. Now there are a number of other identities besides, like we would think tangent equals sine over cosine. Well, let me be specific. Tangent of x equals sine of x over cosine of x. That's a quotient identity or a ratio identity. And as it turns out, the hyperbolic version of that is what we would expect. And so like the reciprocal identities to the right, that's kind of what we expected because that's what happened with the regular trig functions. The hyperbolic trig functions have identities very much like the ones for trig functions. But there are a few that are kind of different. So let's talk about, for example, if we had hyperbolic cosine squared of x minus hyperbolic sine of x squared. By definition, and this is why you would need to know those two definitions, hyperbolic cosine of x is e to the x plus e to the opposite of x over 2, and we're squaring that, minus, and then hyperbolic sine of x is e to the x minus e to the negative x over 2, and we're squaring that. And if you square the numerator of each of those, you'll get e to the x plus 2 plus, oops, I forgot something. I messed up. I'll just back up. That's e to the 2x because we get that squared, plus 2 plus e to the negative 2x, and over 2 squared is 4. And this one becomes, well, I don't need that parenthesis, I guess. E to the 2x minus 2 plus e to the negative 2x all over 2 squared, which is 4. Now doing the subtraction, e to the 2x minus e to the 2x is 0. 2 minus negative 2 is 4. E to the negative 2x minus e to the negative 2x is 0. So the numerators basically cancel out except for the 2 minus negative 2 is 4 over our denominator 4, and that's 1. And so that means that this is a hyperbolic trig function identity. Hyperbolic cosine squared of x minus hyperbolic sine squared of x equals 1. Okay. So if you're asked to prove one of these, this is the type of proof you'd want to do. Start with, say, the difference of those two squares, substitute with their definitions, and or use identities from the 6 things above, and simplify until you get what it's supposed to be equal to. So if you look at the next page, you'll see hyperbolic identities. let me see. Okay, so if you turn to the next slide, there's a list of hyperbolic identities. I'd like for you to get a page of the regular sine, trigonometric identities and kind of compare them and see which ones are like exactly the same, but an H is in there, and the ones that are slightly different, like it's plus when you would have expected a minus or something like that. And just pair them up side by side and see how well they play out. I don't necessarily want you to memorize these identities. I might ask you to prove one, like I proved that hyperbolic cosine squared of x minus hyperbolic sine squared of x equals 1. I may ask you to be able to do that, but I won't ask you to have a bunch of these memorized. Now you should look at the next slide now and look at the derivatives and integrals involving them. And again, do that side-by-side comparison. Like the derivative of regular sine is equal to cosine of your argument. And the antiderivative of cosine of your argument, dx, is the sine. So that looks the same, but notice the derivative of cosine is not negative. So that's a difference. That's something you got to pay attention to. So these derivatives and antiderivatives, I really do want you to know these. And so I would pay attention to theorem 5.20 and spend some time on that, because I would expect that you know those derivatives and antiderivatives. All right, so let's work a few problems that are examples of what we were just talking about, and see how we can apply those derivative and antiderivative rules. So the first question is, what is the derivative with respect to x of hyperbolic sine of x squared minus 3? So the derivative of sine is cosine, so we're expecting to see hyperbolic cosine. And if I slip and say just cosine or just sine at this point, I mean hyperbolic cosine of, it's a real mouthful. Hyperbolic cosine of that argument, and then the chain rule still kicks in, so that'll be multiplied by the derivative of the inside function. The derivative of x squared minus 3 is 2x. All right, B. The derivative of the natural logarithm of a hyperbolic function, in this case hyperbolic cosine of x. Well, the derivative of the natural log of something is still 1 over that something times the derivative of that something, and the derivative of hyperbolic cosine of x is hyperbolic sine of x, which means that we get hyperbolic sine of x over hyperbolic cosine of x. And anything like this that's easy, that I would expect you to know, like those definitions of hyperbolic sine and hyperbolic cosine of x, as well as the identities for the other 4 in terms of hyperbolic sine of x and hyperbolic cosine of x. So in other words, I expect that you would be able to rewrite this as hyperbolic tangent of x. Okay. So those identities, the reciprocal and quotient identities, I do expect you to know. They're in that same set where the definitions were to be found. Okay, so let's do another one. The derivative with respect to x of x times hyperbolic sine of x minus hyperbolic cosine of x. Okay, well, the first thing I see there is a product, so I do have to use the product rule. So that's first times the derivative of the second the derivative of hyperbolic sine of x is hyperbolic cosine of x, first times the derivative of the second, plus second one, hyperbolic sine of x, times the derivative of the first one. The derivative of x is 1, minus the derivative of hyperbolic cosine of x, which is hyperbolic sine of x, and simplifying, you're left with x times hyperbolic cosine of x. Okay, D, example D. We're asked to find the derivative with respect to x of the binomial x minus 1 multiplied by hyperbolic cosine of x minus hyperbolic sine of x. So the first, of course, is a product, so we'll do the product rule. First times the derivative of the second. And you have to really make yourself not write a negative there because the derivative of cosine itself is negative sine of x, but the hyperbolics is a little bit different, so really pay attention to that. Anyway, first times the derivative of the second plus the second times the derivative of the first, and the derivative of x minus 1 is just plain 1, minus the derivative of hyperbolic sine is hyperbolic cosine of x. And simplifying, we're left with x minus 1 times hyperbolic sine of x. Okay. Then we get to talk about the inverse hyperbolic functions. Unlike the trig functions, hyperbolic functions are not periodic. And so if you look at those graphs of those 6 hyperbolic functions, 4 of them are actually already one-to-one. Hyperbolic sine, hyperbolic tangent, hyperbolic cosecant, and hyperbolic cotangent. The 2 that aren't are hyperbolic cosine and hyperbolic secant. So the first 4 that I mentioned have inverse functions without any change in domain. The other 2, hyperbolic cosine and hyperbolic secant, are one-to-one when their domains are restricted to the positive real numbers, and for this restricted domain, they also will have inverse functions. So if we turn to the next slide, because the hyperbolic functions are defined in terms of exponential functions, it's not surprising to find that the inverse hyperbolic functions can be written in terms of logarithmic functions, because of course the inverse of e to the x is ln of x. So inverse hyperbolic sine of x, that's a mouthful. Inverse hyperbolic sine of x is ln of x plus the square root of x squared plus 1, and its domain is all real numbers. And so I'm not going to read all of them to you. So you can see what they are. This is not something I'm going to expect that you would memorize. But do pay attention to the domain restrictions. Those are only valid on those domains. That those will be what the inverse hyperbolic trig function would be. So in the next slide, you'll see the graphs of those inverse hyperbolic functions. Just take a look at them. That's basically every graph reflected over the line y equals x, except for the 2 that were not one-to-one, and it's only the right side of those was reflected over the line y equals x. And one of the things that's interesting about this in the real world of applications, the inverse hyperbolic secant can be used to define a curve called a tractrix or a pursuit curve. So to see how that works, look at example 5. If you are standing on a dock and you have a rope tied to the front of a boat, and you start walking along the pier, then the boat will take a path that is a tractrix. And they give you the equation of that tractrix right there. Notice it involves inverse hyperbolic secant of x. Well, it's x over a, where a is the length of the rope. So let's look at this one and see if we can answer this question. For a equals 20 feet, find the distance the person must walk to bring the boat to a position 5 feet from the dock. Okay, so I'm going to kind of try to start this by drawing a picture that's like, oops, got that in the wrong place. It's like their picture so that I can refer to things. So let's say you started here and walked this way. Oops, well, maybe not that snaky of a path. You're supposed to be walking along the pier. So say you're walking, oh wow, well, I'm not going to worry about that too much. Okay, so you're walking along the pier, and the boat was originally here. Okay, and since you were holding the rope when it's in its initial position, this is the boat's initial placement, this distance is 20 feet. Okay, and the path that it's going to follow looks like this, sort of. And it's that tractrix path I was telling you about. And at any point, when the tip of the boat is, say, right there, that's at some xy pair, some point. If this is the x-axis and this is the y-axis, we can find the coordinates of that point xy using the equation given for the tractrix that involves the inverse hyperbolic secant of x over a, that one. Okay, so we're trying to find how far along the pier the person has to walk. So we're trying to find how far are they going to walk, which is this distance, so that when they've gone that distance, the distance between the pier and the boat is 5 feet. Okay? All right. So, the distance that the person will have walked is, if I forgot to label a point, so let me label this. Let's say that that the point where this happens right here is at 0, comma y1. And so, if this is where y is, right here, that's the y coordinate of that point at some random point. The y sub 1 distance is going to be the y, this part of it, plus another amount. So that's the y part, and this is the unspecified amount that we're going to go. So if we were to draw in, let me get a different color here, draw in, there's a triangle right here. Where question mark is one of the legs of that right triangle. And so if we pull that right triangle out, this is the part that we're needing to know. this is x at that point for that triangle. This point right here is x away from the pier. And of course the length of the rope is always 20, so the distance between the person holding the rope and the boat's down here, and this is the person holding the rope up there, that's always going to be 20 for this situation. So if we use the Pythagorean theorem, that means that x squared plus question mark squared is 20 squared. And so question mark squared is 20 squared minus x squared. And so that question mark length is the square root of 20 squared minus x squared. Okay. So the distance the person's going to walk, that y sub 1 distance, is marked over here with a green question mark. That is what we're calling y sub 1, the point where we are when the boat is 5 feet from the dock. That y sub 1 is the y coordinate where it is at some random point plus the pink question mark, which we just simplified or found to be this radical expression. Okay? And that y, of course, is governed by the equation that was given for this tractrix. So by substitution, I'm going to take out the y and put in its place a, which in this problem is 20, so 20, inverse hyperbolic secant of x over a, so x over 20, because this rope is 20 feet long for this problem, minus the square root of a squared, so a again is 20, so 20 squared, minus x squared, and that's that equation up above with 20 substituting in for each of the a's, plus that pink question mark part that is written in red above, 20 squared minus x squared under the radical. And simplifying, you have some like terms that cancel each other out. You end up getting just this expression. So what we want is for x, the distance that the boat is from the dock, we want that to be 5. Okay, so let me clarify that. The coordinate of this point is 5, comma, y sub 1. And that pink point, remember, 0, comma, y sub 1, that's the intercept at the point. That's where the person is holding the rope, is at that pink dot. Maybe it's red. Anyway, at that dot up there at the top on the y-axis, that y-intercept. Okay, so we want to find out what y sub 1 is when x is 5. So, by substitution, this y sub 1 will be 20 inverse hyperbolic secant of 5 over 20. And then if you look at the theorem 5.21, again, that's not something I would ask you to memorize. Look at the second to last entry. Inverse hyperbolic secant of x is defined as ln of 1 plus the square root of 1 minus x squared, and we've already decided we're letting x be equal to 5, divided by x, which again we've decided is equal to 5, hold on, I think I made a mistake. Yeah, x is 5, but we're taking inverse hyperbolic secant of 5/20ths. So everywhere where I just wrote a 5 should be 5/20ths. So let me just erase that and redo that part of it. So yeah, the input is basically 1/4. So let me go back and fix that. Sorry about that. So instead of 5, this should be 1/4 squared over 1/4. You see why I saw that, because I was about to do 1 minus number way bigger than 1 and get a square root of a negative number, which would not have been a happy place to be. All right, so anyway, and of course that's good because remember this number, according to that domain statement, has to be between 0 and 1. And of course 1/4 is good. It's between 0 and 1. So it's definitely something we can use here. So if you put that in your calculator, you'll get something that's kind of close to 41.27. And of course the units here is feet. So the person's going to have to walk about 41 1/4 feet. And at that point in time, the boat will have moved in to be 5 feet away from the dock. Okay, good. Now, the next thing, differentiation and integration of inverse hyperbolic functions. The derivatives of the inverse hyperbolic functions, which resemble the derivatives of the inverse trigonometric functions, are listed in the next theorem, Theorem 5.22, on the next slide, and the corresponding integration formulas in logarithmic form. So look at Theorem 5.22, and those are the derivatives of the inverse hyperbolic trig functions. Do notice how close they are to the corresponding inverse trigonometric functions. And notice too that there's only one form for those 6. If you have something that looks like the top pair, u squared plus or minus a squared, that would be either inverse hyperbolic sine or inverse hyperbolic cosine. You're just going to use the one idea. And so just like what we did with inverse trig, there are only 3 antiderivatives. And again, these are things I really don't want you to memorize, although I think it's nice if you realize how closely they resemble stuff we've already talked about. So let's do a couple of problems with this and call it a day. So the derivative with respect to x of inverse hyperbolic sine of 2x. Looks like the chain rule is going to come into play. That's going to be 1 over the square root of our input 2x squared plus 1 times the derivative of the inside function, so times 2. And so that answer is 2 divided by the square root of 4x squared plus 1. And unlike numbers, like if I have a problem where there's a radical of a number in a denominator, I certainly want you to rationalize that. But new thing, I may have mentioned this before, but new thing, if it's the square root of a expression in x, you may leave it unrationalized. That final answer is just fine with me. Okay, so now let's Let's do another example. This is inverse hyperbolic tangent of x cubed. So looking at that derivative rule, it's going to be 1 over 1 minus u squared times the derivative of the inside function. And of course, the derivative of x cubed is 3x squared. And so this simplifies to be 3x squared over 1 minus x to the 6th. And that ends this lesson. I will see you in class.